So you have already heard a lot from me. Let's now move forward and take a closer look at how it all works. As mentioned earlier, Woodward and Inventor provide tools for calculations, allowing us to determine contact areas and create coordinate systems. Within these parameters known, we can implement adaptation mechanisms to insert and properly position hardware components. Furthermore, you can access these parameters and utilize them in a logic code for your own applications. So as you can see, our main discussion object is a contact area. All objects are related to it. What does Woodward and Inventor know about connections? Here are two types. First one, edge-side. This occurs when one board connects to another by using the end of the board and touching the side of the other. The second one is edge-edge type. This occurs when two boards are connected using their edges. As demonstrated in my examples, we are not limited by angles or thicknesses of the board. They can vary. Here, I would like to pause and highlight other parameters used and accessible for connections. As you can see, we have two board connections, and right now we have two connection areas, contact areas. So what do we know? We know contact area properties like length and width. Also, we know contact angle, connection angle, and contact angle. Additionally, we know nested board thickness and pillar board thickness, and possibly others in the future, of course, because smart hardware feature is developed rapidly, and it might be that some features will be included in the future. So let's proceed and examine this simple example. For the sake of simplicity, I will be using the well-known graphics connector. It consists of two components, a connecting bolt and a housing. These are assembled into one design and one assembly in Inventor, and you can see how this component is used in the picture right now. So we are basically connecting two boards which are connected perpendicularly. So let's take a look at this video, and I will demonstrate the insertion process of the graphics component, smart graphics component. I have a simple box with different contact areas on the side. And using standard attach command, now I'm inserting a graphics component using from our library. As you can see, I can define the insertion direction. This is crucial for components like graphics, minifigs, and many others. And right now I am selecting participating boards, and as you can see, I don't need to specify which board is which. Everything will be done automatically. Just click OK. And with a bit of magic, after a couple of seconds, all components are inserted according to the rules. So let's check the situation. As you can see, all boards have connectors, and they are placed according to the rules which are embedded in a graphics connector. The quantity varies depending on the length of the contact area. Let's check the situation using wireframe mode. Everything seems all right. Here you can see what has been accomplished and the principles that we employ. On the right, I have similar example when two boards are connected using the same graphics connectors, and as you can see, this is the sketch, and this sketch represents a contact area. And I have some parameters like length, width, and others. So, after the insertion and analysis of contact area, we apply and update several parameters embedded in a graphics, such as contact area length and width, offset values. Knowing these parameters, we can update placing length. We can control maximum distance between components and others if they are included in a logic. So let's check more details, and these details will be provided in the next slide. Let's take a look at simplified scheme of how smart hardware components are constructed. In the main assembly, we add at least two crucial components, the skeleton and the hardware component. The skeleton component controls placing geometry, incorporating various rules and formulas to manage placing parameters. Typically, contact area and other properties are extracted to this file. Here you can see the usage of logic rules, control sketches, and parameters. A hardware component is usually an assembly or assemblies of thought. It can sometimes be a single part or few of them. These components represent the hardware element. They contain hardware geometry, BOM information, and can be controlled by the main assembly by transferring various parameters. Those properties should be selected in a model state if used. Hence, we may or may not have logic rules, model state features, and other meta properties here. The main assembly combines all elements into one and is selected when placing the smart hardware component via attach command. Keep in mind that all mentioned elements are simplified and can vary depending on the hardware. For example, for a handle, it will consist of a skeleton and a part, but for a hinge or any other complicated component, the structure may differ. Specific examples are provided with our installation, so please take a look at them. As mentioned earlier, all smart hardware components utilize simpler or more advanced logic, implemented in several ways. Through iLogic or using geometry as sketch. However, ultimately, all these values are written in inventor's parametric table. Moreover, you can use iLogic forms for finer control of components. For instance, if you wish to control the quantity of the inserted components, you can do so through a form. Once again, I would strongly recommend analyzing the samples we provide with our installation.